Look up for a moment. You have done it thousands of times in your life, yet you have never truly questioned the absurd physics unfolding above your head. You were taught a simple truth since childhood. Gravity is the unbreakable force of this planet, pulling everything without exception toward the center of the Earth. Drop a stone, it falls. Jump, you return, everything obeys it, always, without mercy. So now answer something that should disturb you more than it does. If gravity is truly absolute, then why doesn't the sky collapse onto your head right now? You look at a cloud and your mind tells you it is light, soft, almost imaginary like floating cotton. But that is not what it really is. A cloud is not illusion, it is water. And water is heavy. A single ordinary storm cloud can contain over 1,000,000 kilograms of mass suspended above the ground. 1,000,000 kilograms of liquid water and ice crystals hanging quietly in the sky. If you place that same mass in steel on the ground, it would crush buildings instantly. Yet up there, it simply stays. This is where intuition fails completely. Human perception was never designed to understand the deep mechanics of nature. It evolved to avoid danger, not to decode the structure of reality. And if you want to understand why 1,000,000 kilograms of water does not fall on your head every second, you must first destroy the childish image you have of a cloud. A cloud is not a solid object. It is not a floating sponge or a shaped mass drifting in the air. It is something far stranger. It is an enormous swarm of microscopic droplets and ice particles, each separated by vast volumes of air. Trillions upon trillions of tiny spheres, all interacting, all suspended in constant motion. And here comes the first uncomfortable truth. The cloud is not floating, it is falling. Every single particle inside it is being pulled downward by gravity at this very moment. Gravity does not pause at a certain height above Earth. It acts everywhere, constantly, with the same cold consistency. So why doesn't it crash? Because another invisible force is at work, and it operates at a scale your senses cannot perceive. As these microscopic droplets fall, they move through air, not empty space, but a dense, chaotic fluid made of nitrogen and oxygen molecules packed tightly together. To fall, each droplet must push these molecules aside, colliding with them constantly. That creates resistance, and resistance pushes upward, opposing gravity. A large raindrop falls quickly because its mass is concentrated and can overpower air resistance. But now, imagine that same drop shattered into millions of microscopic fragments. The total mass is unchanged, but the surface area explodes dramatically. Suddenly, the air has far more surface to push against. The droplet is no longer a heavy object. It becomes a suspended particle trapped in a balance between gravity pulling down and air resistance pushing up. At this scale, something strange happens. The droplet reaches what we call terminal velocity, a state where forces balance perfectly. It stops accelerating downward and drifts at an almost absurdly slow speed, millimeters per second. To your eyes, this looks like stillness, but in reality, the cloud is collapsing slowly, constantly dissolving and reforming. A silent, invisible rainfall frozen in time by scale alone. Yet even this explanation is incomplete, because if everything is falling even slowly, then logically the entire cloud should eventually reach the ground. So why does it remain suspended for hours, even days, without collapsing? This is where the story deepens, and where the atmosphere reveals itself not as a passive background, but as an active, violent system powered by energy from something far above you. The real answer is not in the droplets themselves, but in the invisible motion of the air surrounding them. And that motion begins with a force so powerful it drives every storm on Earth. To understand what truly holds a cloud in the sky, you must stop thinking of air as empty space. It is not empty. It is a dense, moving fluid constantly in motion, shaped by energy arriving from 150 million kilometers away. Everything begins with the Sunday. Solar radiation travels across the vacuum of space and strikes the Earth's surface with relentless intensity. The ground absorbs this energy, heating up, and then transfers that heat directly to the air resting above it. And here the real transformation begins. When gas is heated, its molecules gain energy. They move faster, collide harder, and push each other apart with increasing force. The air expands, but expansion comes with consequences. As it spreads out, its density drops. It becomes lighter than the colder air around it. Now imagine vast invisible bubbles of warm, low-density air forming near the surface. Surrounding them is colder, heavier air pressing down. Physics does not tolerate imbalance for long. The lighter air is forced upward. This is buoyancy, an invisible engine driving motion across the entire atmosphere. These rising columns of warm air do not move gently. They surge upward at speeds of several meters per second, carrying moisture, heat, and instability into the upper atmosphere. This is not calm air. It is a continuous vertical engine powered by solar energy. Now connect this motion to our falling cloud droplets. Earlier, We established that microscopic droplets are constantly drifting downward due to gravity, but they are falling at speeds so slow that they are essentially suspended. Millimeters per second versus meters per second. And here lies the crucial imbalance. While droplets attempt to fall, powerful updrafts of warm air are rushing upward beneath them. These rising currents are far stronger than the droplets' downward drift. The result is not equilibrium, it is domination. Picture an escalator moving upward while you try to walk downward at a slow pace. From your perspective, you are moving, but relative to the ground, you are being lifted. The cloud is exactly this system. Trillions of particles trying to descend through an atmosphere that is actively pushing them upward. This is why clouds do not collapse. They are trapped inside a constantly moving thermal engine, a battle between gravity and heat-driven convection that never stops as long as the sun shines. But this creates a deeper problem. If warm air keeps rising, pushing moisture upward indefinitely, then logically clouds should keep ascending endlessly, eventually reaching space. Yet they do not. They stop, they flatten, they spread. They hit an invisible boundary in the sky as if they have collided with something solid. And that raises a new question. What exactly stops this vertical ascent? What invisible structure forces the atmosphere to change behavior so abruptly? The answer lies higher above, where temperature itself begins to reverse its rules and where the atmosphere transforms into something entirely different. If warm air is constantly rising like an unstoppable elevator, then logically clouds should keep going higher and higher until they escape the planet entirely. Nothing in the previous explanation suggests a natural stopping point, yet reality disagrees completely. Storm clouds do not rise forever, they stop, and more strangely, they flatten into a dramatic, anvil-like shape, as if they have collided with a hidden ceiling in the sky. To understand this, you must follow that rising column of air as it travels upward. At the surface, it is warm, energetic, and buoyant. It rises quickly, expanding as it moves into regions of lower pressure. But this expansion comes with a cost that is often ignored in simplified explanations of weather. As a gas expands, it must push against the surrounding atmosphere. That pushing requires energy. Since no external energy is added during the ascent, the gas pays the price using its own internal heat. This leads to a process called adiabatic cooling. In simple terms, as the air rises, it loses temperature. The higher it goes, the colder it becomes. This is not a gradual suggestion of physics. It is an unavoidable consequence of thermodynamics. The rising air is constantly trading its heat for expansion, draining its own energy to continue moving upward. Eventually, something critical happens. The rising air cools until it reaches the same temperature as the surrounding atmosphere. At that point, the density difference that was driving the ascent disappears. The buoyant force collapses. The vertical motion stops. But this still does not explain the dramatic shape of storm clouds. Why the flat top? Why the sharp boundary, as if the cloud has hit a solid barrier? To answer that, you must look even higher, into a region of the atmosphere where the rules of temperature completely reverse. Above roughly 10 to 12 kilometers, the structure of the atmosphere changes. This region is the stratosphere, and within it lies something crucial, the ozone layer. Unlike the lower atmosphere, where temperature decreases with altitude, the stratosphere behaves differently. Here, temperature increases as you go higher. The reason is absorption of ultraviolet radiation by ozone molecules. This energy heats the surrounding air, creating a warm layer above a cold one. Now imagine the rising cloud reaching this boundary. Below it is cold, dense air continuing its upward motion. Above it is a warm, stable layer resisting vertical movement. The cloud tries to push upward, but it encounters increasing resistance. It cannot break through easily because the surrounding air above is not just colder or lighter, it is dynamically stable. The energy required to continue rising becomes too great. The upward motion is forced to slow, then stop entirely. So what happens to all that rising moisture and energy? It has nowhere to go but sideways. The cloud spreads outward, flattening violently against this thermal boundary. This is why thunderstorm clouds form their iconic anvil-shaped wide, flat tops that look like they have struck an invisible ceiling. What you are seeing is not a solid barrier, but a thermodynamic transition zone, a region where buoyant forces lose their authority and atmospheric structure reorganizes itself. At this point, the system seems complete. We understand how droplets resist falling, how warm air lifts them, and how the atmosphere eventually stops that ascent. But there is still a missing piece, one that completely challenges the model we have built so far. Because everything we have described depends on one assumption, that clouds are made of water droplets existing safely at high altitudes. But there is a problem. At those heights, temperatures drop far below freezing, sometimes down to -30 or even -40 degrees Celsius. According to simple logic, Liquid water should not exist there at all. It should freeze instantly, turning clouds into solid ice masses that fall violently to Earth. Yet when you look up, clouds are not solid ice. They are not frozen blocks. They are fluid, shifting structures. So the question becomes unavoidable. How can liquid water exist in conditions that should instantly freeze it? The answer to this question will completely break your assumptions about matter itself, and it leads directly into the hidden physics of clouds that almost nobody ever truly understands. And that is where everything becomes even stranger. At first glance, the rule seems absolute. Water freezes at 0 degrees Celsius. It is one of the most basic facts taught in school, repeated so often that it feels like a law of reality itself. But the atmosphere does not care about simplified classroom rules. It follows deeper physics, and those rules reveal something far more unsettling. If you climb into a thunderstorm cloud, you will find temperatures of -20, -30, even -40 degrees Celsius. And yet, the cloud is not made of solid ice. It is still composed largely of liquid droplets. This is not a contradiction. It is a failure of our intuition. To understand this, you must stop thinking of freezing as a simple switch. Water does not instantly transform from liquid to solid just because a temperature threshold is crossed. Phase change is a process, and it requires a starting point. That starting point is called the nucleation site. In everyday life, water is full of impurities, dust, minerals, microscopic particles. When water cools, these particles act as anchors. They give water molecules something to attach to, allowing the crystal structure of ice to form. Once crystallization begins, it spreads rapidly, and freezing appears instantaneous. But inside high-altitude clouds, conditions are radically different. The water droplets are extremely pure, almost perfectly clean at a molecular level. There are no dust particles, no structural impurities, nothing for ice crystals to begin forming around. So even though the temperature is far below freezing, the water has no instructions on how to become ice. The molecules slow down, lose energy, and reach a state where they should freeze, but they cannot organize themselves into a solid structure. This creates a bizarre state of matter known as supercooled water. It is still liquid, but it exists in a fragile, unstable condition, balanced on the edge of solidification. It is like a system waiting for a trigger that never comes. But the danger lies in how easily that trigger can appear. If a tiny dust particle, a cosmic fragment, or even an ice crystal enters the cloud, it becomes a seed. The supercooled droplets instantly latch onto it. In milliseconds, water transforms into ice, releasing energy and forming a solid structure almost explosively. This is not a gentle process. It is one of the fastest phase transitions in nature. Now consider what this means inside a cloud. You have millions of kilograms of supercooled water suspended in a delicate, unstable state. A single microscopic disturbance can trigger rapid freezing in localized regions. This is one of the reasons aircraft passing through storm clouds can experience sudden ice buildup on wings, because the system is primed for instant transformation. But even this does not fully resolve the life cycle of clouds, because once ice forms, it does not simply stay suspended, it begins to grow. And that growth leads to one of the most aggressive and silent processes in atmospheric physics, a process where water molecules are effectively stolen from one particle and transferred to another, turning microscopic ice crystals into massive structures capable of breaking through the entire atmospheric balance and collapsing back toward the ground. Inside the cloud, something far more violent is happening than most people ever imagine. It is not just water floating in air. It is not just ice forming and falling. It is a microscopic economy of growth, theft, and imbalance where matter is constantly redistributed according to strict physical laws that feel almost unfair. At these freezing temperatures, two states of water coexist: supercooled liquid droplets and tiny ice crystals. They occupy the same space, drifting side by side, but they are not equal in behavior. And in physics, inequality always leads to motion. The key to what happens next lies in something invisible: water vapor. The air inside a cloud is saturated with it, meaning it is filled with water molecules constantly moving between droplets, ice crystals, and gas form. Nothing is truly stable. Everything is exchanging material at a molecular level. But here is where the system becomes unbalanced. Ice has a structural advantage. Its crystalline lattice holds water molecules in a more stable configuration than liquid water can. Because of this, ice can attract and lock in water vapor more efficiently than liquid droplets can retain it. So while liquid droplets and ice crystals sit close together, a silent transfer begins. Water molecules evaporate from the liquid droplets and immediately attach themselves to the ice crystals nearby. No physical contact is needed. The air itself becomes the transport system. This process continues relentlessly. The liquid droplets slowly shrink, losing their mass molecule by molecule. At the same time, the ice crystals grow larger, accumulating material from their surroundings. What appears to be a calm cloud is actually a one-sided exchange, where liquid water is gradually erased and rebuilt as ice. This mechanism is known as the Bergeron process, and it is one of the most important engines behind precipitation. As time passes, the imbalance increases. Ice crystals grow from microscopic fragments into visible structures. They begin to develop mass, shape, and gravitational influence. And once they reach a certain size, the balance that kept them suspended begins to fail. Gravity, which was once neutralized by air currents and microscopic scale, starts to regain control. The ice crystals begin to fall. At first, they are still small enough to be carried upward by weak air currents. But as they continue collecting material, they grow heavier and heavier. Eventually, their mass becomes too large for the upward flow of air to support. The equilibrium breaks. Now the cloud has entered a new phase. What was once a suspension of microscopic particles becomes a structured system of falling bodies. The ice crystals accelerate downward, passing through warmer layers of air beneath the cloud. And as they descend, another transformation begins. Heat from the lower atmosphere begins to act on them. The rigid crystalline structure of ice starts to collapse. Molecular bonds break. Order dissolves into chaos. The ice melts, transitioning back into liquid water. By the time it reaches the ground, what was once a fragile ice crystal high in the atmosphere has become a heavy droplet of water falling under full gravitational control. That is the complete vertical journey. Vapor becomes droplets, droplets become ice grows by stealing from liquid, and finally returns as rain. But even now, the system is not fully explained. Because this entire structure depends heavily on freezing temperatures and ice formation, it assumes that cold clouds dominate the process of precipitation. Yet there is another environment on Earth where clouds behave completely differently. A place where temperatures remain warm from ground to sky, where ice plays almost no role at all, and yet storms are even more intense, more violent, and more destructive. The tropical regions of our planet, here, the physics of rain changes completely, and the mechanism that produces rainfall in these conditions is even more aggressive than anything we have seen so far. In the tropical regions of Earth, the atmosphere behaves like a completely different machine. The surface is heated intensely by the sun, and this energy drives massive amounts of air upward with extraordinary force. Warm, moisture-rich air rises continuously, feeding enormous cloud systems that can span entire regions. But unlike the colder parts of the atmosphere, these clouds never drop below freezing. There is no ice phase dominating the system, no crystals growing silently through molecular theft. Yet the rainfall here is often more intense, more sudden, and far more destructive. So the question becomes unavoidable. If ice is not involved, how does liquid water still grow large enough to fall? The answer lies in something much simpler and far more brutal. Collision. Inside tropical clouds, water droplets are constantly forming at slightly different sizes. This variation is unavoidable because the cloud is built from countless microscopic particles acting as condensation points. Some droplets form slightly larger, others slightly smaller. This difference, even if extremely small, determines their fate. A larger droplet has slightly more mass. Because of that, it falls through the cloud just a little faster than the smaller droplets around it. This difference in speed is tiny, but in a dense cloud environment, it is enough to trigger continuous interaction. As the larger droplet moves downward, it collides with smaller droplets in its path. And when these droplets meet, they do not bounce apart. They merge instantly due to surface tension. Each collision adds mass to the falling droplet. This process is called coalescence, and it is the foundation of tropical rainfall. But what makes it truly powerful is feedback. As the droplet grows larger, its mass increases, which increases its falling speed. As it falls faster, it collides with even more droplets per second. Each collision makes it heavier, which makes it faster again. This is not a linear process. It is exponential. A self-amplifying cascade of growth, driven purely by gravity and fluid dynamics. What begins as microscopic droplets suspended in warm air becomes, within minutes, a rapidly accelerating sphere of water accumulating mass from everything it encounters. Eventually, it becomes too heavy for the surrounding updrafts to support. At that point, the balance collapses. The droplet breaks free of the cloud system and begins its descent toward the ground at full speed. It falls through layers of air that are increasingly warm and dense. If it becomes too large, aerodynamic forces begin to tear it apart, fragmenting it into smaller droplets midair. But each fragment continues the same process, rapidly rebuilding mass through further collisions. What reaches the ground is not a gentle or delicate process. It is the final result of a runaway mechanical system powered by gravity, heat, and constant molecular interaction. And now, after following every stage from invisible vapor to unstable droplets, From frozen crystals to tropical collisions, you finally see the complete structure of a cloud. It is not a soft object. It is not a symbol of calm skies. It is a dynamic system of balance and failure, constantly fighting between upward thermal energy and downward gravitational collapse. A temporary equilibrium built on forces so large and so precise that they hold millions of kilograms of water suspended above your head every second of your life. And when you finally understand that, the sky is never the same again. Because what you are really looking at is not weather. It is physics made visible.